stage is yours.
Okay, thank you very much. It's a great pleasure to be back here, traveling again after the pandemic and back to a place that I've spent some time in the past. And so thank you very much for the organizers for all their great organization and putting together this exciting program. What I'm going to talk about today is causal models with fine-tuning and cycles and their compatibility with spacetime. So this is a way to go beyond what might be considered the normal causal modeling framework, which normally assumes that you don't have fine-tuning and you don't have cycles. And we just want to ask, well, can we extend the modeling to this? How should we do so, and what interesting things happen when we do so? And yeah, I should mention that this is based on these two papers here, which is joint work with Felicini, who of course everybody knows. And actually she did a lot of this work as part of her PhD thesis when she was in York. Okay, so as was mentioned earlier, there are many different notions of causation. I'm going to focus on, well, this is the theme of the conference. I'm going to focus on two of these. The relativistic notion, which I've just drawn a sketch of here. So in the relativistic notion, we have these events. They may be associated with some random variables. Here I've just got A, B, C, and D. And the usual relativistic notion of causation might be that, well, for each of these events, we can draw some notion of its future, a future light cone. And the idea is that the future light cone doesn't necessarily dictate exactly what causes what, but it gives some constraints on what causes what. Namely, if one event causes another, the second event ought to be in the future light cone of the first. So in this diagram, as I've drawn it, we would be fairly happy if D was caused by A, but not so happy if C was caused by A, if you like relativity theory. Okay, and the alternative is a kind of more sort of, I call it the causal model notion of causation. So this is where you really try and say exactly what causes what. So now the fact that there's an arrow from A to D doesn't just mean that A has the potential to be a cause of D, as it would by saying D is in the future light cone of A, but it actually says that by drawing the arrow in the causal modeling framework, I really want to make the claim, whatever that means, but that A really is a cause of D, for instance, and that B here is a cause of C, and so on. Okay, and here's another possibility that we might not be so happy with. So if we at least imagine these variables having the spacetimes locations as shown above. Okay, because here I've drawn an arrow from A to C, but if these are the locations in some kind of spacetime, then we might be a little bit less happy about having an arrow from A to C. Okay, and this is kind of questions we want to ask. When should we or when should we not be happy with these kind of things? And if I add another variable here, E, now we could have a situation where, for instance, A could be a cause of both E and C in such a way that actually there isn't a possibility of signaling from A to C. Okay, so I'm going to explain a bit more about this later. This is what's known as a jamming correlation, but this is why we might be interested in this. So it might be that we could have causation, perhaps without it implying necessarily signaling, and if we have causation that doesn't imply signaling, we can get sort of parts of relativity back, but maybe not others. And so this might be an interesting playground to think about for causal modeling. Okay, so these are the two notions that I'm going to think about here, and I want to treat them relatively independently, but then try and find a way to unite them. So we ask the question, is there a way to have causal models with superluminal causation? So we might allow this notion of causation, and we might even potentially want to think about, could there even be causal cycles? So is there a reasonable framework in which we could even have cyclic causation? Okay, but maybe we don't want to, as soon as you start introducing causal cycles, this potentially leads to paradoxes. We don't really want these paradoxes, so we'd like to at least keep some aspects of relativity theory, and we're trying to do that in order to not get into too much trouble. And so we say, well, can we keep some aspects of relativity, for example, that there's no superluminal signaling? Okay, so this is what we want to do. And the first observation is, well, if you're willing to have superluminal causation without signaling, you necessarily need a notion of fine-tuning, or alternatively, this is sometimes called lack of faithfulness. So we're going to have to upgrade our usual way of doing causal models to allow for that. And secondly, we're going to have to, or we're going to need to disentangle the causal model from the relativistic notion. Okay, because if we sort of take the relativistic notion that will just say, well, you can only have causation into your future light cone, then immediately we're not going to be able to have things like cycles straight away. Okay, so we're going to have to adjust and modify the framework in order to get this to work. Okay, so this is what I plan to do in this talk. I'm going to start by introducing the usual causal modeling framework as a way to help contrast with what we want to change. So this is really just looking at this second notion, the causal model notion of causation. Then I want to introduce the space-time notion and see how we can merge those together, or potential ways to merge those together. And actually this leads to what you may think of as quite a surprising possibility, that actually we can have some kind of operationally detectable causal loop that nevertheless can be compatible with a Minkowski-like spacetime without leading to signaling. And I'm going to explain that towards the end. Okay, so here's the usual causal modeling picture. So apologies to a lot of people who know that, but I know it's quite a broad audience, and actually also heard some of this morning. But yeah, here's a little refresher for everyone who forgot everything over lunch, or just likes to be reminded of things anyway. Okay, and this comes from, well, this is kind of so well understood that there are books written about it, and even books were written about it more than 20 years ago. So this is a very well trodden ground. So what do? You start off with a directed acyclic graph between observed and potentially unobserved nodes. And in this talk, I'm going to draw observed nodes in circles. So if some node's in a circle, that means it's something that we can see, and unobserved nodes just don't have circles. And actually, here's the example. Here is just what we might draw if we're thinking about the usual bipartite Bell scenario. If we have inputs A and B by Alice and Bob, and they give rise to outputs X and Y, and we posit that there's some kind of causal connection between them. So this represents the entanglement, perhaps if this is non-classical, or if you're thinking about a local hidden variable model, this lambda will be the just a classical random variable that you're probably familiar with if you've ever thought about Bell's theorem. Okay, so the observed nodes are associated with random variables. These are the things we see. These we don't directly see quantum systems, even if we're thinking quantum mechanically. So yeah, they're always associated with random variables. And the unobserved things, this is where we can start seeing the differences between different theories. These may be classical, quantum, or in principle, we can think about other theories. For the purposes of the talk today, I don't want to worry about underlying quantum things. Sorry, I know it's a very interesting topic. We've heard about that a lot this morning. But for the ideas that I need to mention today, it maybe just keeps it simple, given the time available, just to think about these things as classical for the moment. So this is not necessary for the framework, but just for today, think about classical, all the unobserved nodes as also being associated with classical random variables. Okay, and actually if we think about the usual causal modeling framework, that's what people would have thought about. So when Pearl is writing this book, he's not worrying about quantum theory. So maybe I should already be thinking only about classical underlying variables, because I'm anyway talking about the usual causal modeling picture for the moment. Okay, and when you draw one of these diagrams, what this is supposed to encode is that the distribution over the random variables obeys this kind of relation. Okay, so if we have a whole bunch of random variables in our causal structure, x1 to xn, then the joint distribution should be the product of the distributions of each random variable by itself conditioned on its parents, okay, and not conditioned on other things. Okay, so it's encoding a whole bunch of conditional independence relations. So in case you're not familiar with it, if we just apply this to this causal structure that I've drawn here, then what this encodes is that the joint distribution of A, B, X, Y, and lambda should take the following form. It's got a distribution over lambda multiplied by a distribution over A, multiplied by the probability over B, and then we get P of X given A lambda because the parents of X are A and lambda, and Y given B lambda, the parents of Y are B and lambda. Okay, and if you think about just writing out, just expanding out this probability distribution without thinking about the causal structure, then we'd have P lambda, we'd have a P of A given lambda here. And so what writing this Markov condition has encoded is that the distribution of A given lambda is just equal to the distribution of A. Sorry, I don't know why there's that's a comma, not a prime. Okay, and the probability of X given A, B, and lambda is just the probability of X given A lambda. So this is encoding a lot of things, and actually the things that are encoded just by writing down this causal structure are exactly what Bell would have called local causality. Okay, and so this Markov condition is encoding a bunch of independencies. If I just write down an arbitrary causal structure, you could ask, okay, what are the independencies that are kind of contained in there? And there's this nice condition called D-separation, which tells us how to identify, just by looking at the graph, whether there are particular independencies. Okay, I've written the definition here. I think it's not too important exactly what this is. Also, it was mentioned in the morning. The main point is that there is a nice way to look at the graph and decide whether two sets of variables are independent or conditionally independent on each other. Okay, and the idea is that if you have D-separation between variables in your graph, then those variables should necessarily be independent if you have this kind of causal structure. Okay, so in particular, if X is D-separated from Y given Z, then the probability of X, Y given Z should factorize as the probability of X given Z times the probability of Y given Z. Okay, so again, probably a lot of people just know this already, and if you don't know it, you don't need to worry exactly about this condition, but the only thing to say is just that there is a nice way to look at the graph and tell that certain things are independent without doing too much of a calculation. Okay, and so if you start from D-separation, and if you have one of these causal models, then if you have D-separation between variables, you get independence. And the idea behind a faithful causal model is that this should then be an if and only if condition. Okay, so also if you look at the correlations and you see independence, then there should be a D-separation. Okay, so that's one way to explain this, what it means to be faithful, or for the causal model not to be fine-tuned. Okay, so basically there shouldn't be independencies, shouldn't just accidentally happen. They should only happen because there's just no possibility of causation. Okay, but of course we're trying to go beyond that, and maybe to give another kind of little motivation as to why we might want to do this. This kind of lack of faithfulness or this fine-tuning is something that naturally comes about in certain situations, usually, or in almost all cryptographic situations, it's useful to deliberately fine-tune causal links. Okay, so if you want to do a one-time pad, you have a message M, and you have a key K, and you want to make your encrypted message ME. And what you do is you make sure your key is uniformly distributed. And if your key is uniformly distributed, you combine it with your message such that this encoded version of the message gives you no information about the message, okay, which means that it's independent of the message. Okay, so this is a case where, but we know that the message does, well, it seems to be a cause of the encoding, at least when I take the M and the K, I have to combine them in some way to give my encoded information. So we do think that there is a causal link between the message and its encoding, and yet we have an independence there. Okay, so normally if a message is going to, or a variable M is going to be the cause of some variable ME, then we would expect a correlation, but we're deliberately setting this up so that we don't get a correlation. Okay, and another example is so-called secret sharing, or sometimes called the traitorous lieutenant. So if you have a secret M and you basically want to give it out to two people such that neither of them can individually know the message, but if they come together, they can find the message. Okay, and so what you can basically do is you can give a random bit to say one person, and then you can XOR if it's a 1-bit message, with the random bit M1 to give you your M2. And now if these two parties come together, they can again XOR M1 and M2, and that should give you back the M. But again, there's no correlation between M1 and M, or between M2 and M, but these are examples of kind of fine-tuned causation. Okay, but I'm not trying to sort of say that fine-tuning is therefore always a natural and useful thing to do. So it can be useful in these situations, but it's still, I'm also not trying to criticize the way the causal framework has been introduced, because I think it is very natural to assume that there is no fine-tuning in many situations, or to say it another way, fine-tuning without good reason is also a very unnatural thing. Okay, we don't expect things to accidentally sort of not have correlations when things are causing each other. Okay, and actually this is the subject of a paper by Wood and Speckens, which basically say that, well, if we take the usual Bell causal structure and the correlations that violate it from quantum mechanics, then actually we can't find any satisfying classical explanation, whereby satisfying it means that doesn't use fine-tuning. Okay, and so this is really the reason why, in light of Bell's theorem, we'd like to think of other notions of causation in the presence of quantum mechanics. We don't really want to just say, okay, there is the usual notion of causation with fine-tuning. We'd like to upgrade our notions to take care of a more natural quantum notion. Okay, and there may be other things that we might want to think about. So here's a more exotic type of correlation, which is called jamming. Here are two papers that I think it was first introduced in the first of these and discussed in the second one. And what happens here is as follows. So we have three parties, and we have a party who can choose the value of B. And what choosing B does is it either decides whether A and C will be correlated or whether they'll be anti-correlated. Okay, so either A is going to be equal to C, let's say if B is 0, or A and C are going to be different if B is 1. Everything is bits. Okay. And now if A and C are space-like separated from B in different directions, then this is still a way we can still have these types of correlations without having signaling. Okay, so you may be a bit worried, and it is a bit worrying. You should probably be a bit worried that if A is space-like separated with B, but nevertheless, and C is also space-like separated, but the XOR of A and C is always equal to B. Okay, this doesn't feel very nice in terms of our usual notions of causality. In a sense, there is some superluminal causation going on, but it's the kind of superluminal causation that actually cannot lead to signaling. And the reason it cannot lead to signaling, well, it actually depends exactly where A and C are in the causal diagram, but if they are kind of as they're drawn here, then the reason it can't lead to signaling is because for A and C to check, or to check whether A and C are correlated or not, they'd have to get together or send messages to each other, and they would only be able to do that in the future of B anyway. Okay. And so although there is some kind of superluminal causation here, it doesn't lead to signaling. And so we could think of this as now a kind of, we could think of having a different type of theory that goes beyond classical theory and beyond quantum theory, that maybe has these jamming boxes as just natural parts of the theory, a bit like a PR box, but now we could have a jamming box. So we could just have some systems, we posit they exhibit jamming correlations, and now we can think, okay, is that a nice theory? What could we do with such a theory? Okay, so that's another kind of motivation of what we might want to do. Here's the, sorry, I probably should have shown this a few seconds ago. Here's the kind of light cone structure that we might imagine where we wouldn't be able to signal in spite of this being the causal model. Okay, and we also might want to cope with things like causal cycles. Here are two examples. So on the left is actually something that you might even have a model, or is a kind of situation where causal modeling with cycles might be useful. So here we're imagining TO, or we're imagining some kind of thermostat controlling temperatures. TO is the outside temperature, TI is the indoor temperature, and E is, say, the energy used by your heating system. So, of course, if it gets cold outside, this is going to try and cool down the temperature inside. But if you've got a good heating mechanism, the thermostat will control it actually so that the inside temperature remains constant in spite of things happening outside. And so you could say, well, the call for energy is caused by a lowering of the indoor temperature, but then it also feeds back and heats up the indoor temperature. And one way to model this might be with a cycle. Okay, but there could be other situations where we think about cycles. Maybe I've just drawn one here. I don't say now exactly what situation we're necessarily thinking of, but I'll come back to this example later. Okay, so that's the kind of introduction. Now I want to try and say what's going on in the framework. So we'd like this causal modeling framework to allow cycles and a lack of faithfulness, or to cope with fine-tuning. So here's the usual framework, and what we're going to do is we're going to change it essentially like this. So we don't want our graph necessarily to be acyclic anymore, otherwise we're definitely not going to be able to deal with cycles. And the lack of faithfulness basically says d-separation is now not an if and only if with conditional independence, but we are still going to maintain that d-separation implies conditional independence. Okay. All right, so that's just summarize the changes. So now, instead of saying a probability distribution is compatible with a causal model if it satisfies this Markov condition, we say a probability distribution is compatible with this directed graph if whenever you have d-separation, you have conditional independence in that probability distribution. Okay, and now the notion of intervention, which again we heard about this morning, is also going to be very useful in our framework. This is not new to the framework, but also occurs in the standard framework. And okay, just to quickly go over it, if we have a causal graph G, then if we want to intervene on some variable x, what we do is we essentially cut the usual incoming arrow to x. So in this case, we're cutting the arrow from lambda to x. We instead insert a new intervention variable x that basically sets x to some value, and everything else remains the same. Okay, and I have to be a bit careful about what I mean by everything else remains the same, because we don't really necessarily know what's going on. And to think about what it means to be the same, we may imagine that in principle there are some underlying causal mechanisms that are behind the observed correlations. Okay, so in fact there is some function. In the classical case, it will be a function fx. Here I've made it a deterministic function of lambda, but it could also have some extra variables that allow it to effectively be random. And what happens is that these mechanisms continue to hold under the intervention except for the variable that we've intervened on. Okay, so if we intervene on x, we're still going to assign y to be fy of x and lambda. It's just that x is now not dependent on lambda anymore. It just takes some fixed value. And this intervention is in principle, I want to think of it as in principle an operational thing. We can imagine it actually being done. So what happens under intervention, you might be able to just find that out by an experiment. You might be able to go out there, intervene, take statistics, and see what the actual effect is. Sometimes you might not need to do that experiment, and this is the regime of the do calculus, which can relate features of this do graph to those of the original graph. And without going into the details of that, this do calculus relations do continue to hold in this framework. Okay, and we just introduced this terminology of effects. So we say that a variable x affects another variable y if, when we intervene on x, we see a difference. So this distribution is not the same as it was in the original graph. Okay, this is just a terminology, but these kind of effects relations are a kind of useful concept for understanding or to try and whittle out causation operationally if we, say, don't know the underlying causal structure. Okay, and so now we have that causation from x to y does not necessarily imply that x affects y. Okay, that's the kind of different thing. We may now have causation without it necessarily leading to an effects relation. For example, in this one-time pad situation, it's not, although the encoded message is caused by the message, there's no change in distribution here, because essentially the presence of this key will wipe out the correlation that you would otherwise expect to be there. Okay, and without again going into too much detail, one of the main things is that so there aren't just these simple effects relations that I mentioned, but we can also have more complicated effects relations. In a general graph, we might imagine comparing interventions on, say, 3 variables with interventions on those same 3 variables and an extra one, or an extra 2, or something like this. And we may also imagine having extra information around that we can condition on. And I'm just calling these things more complicated effects relations. Okay, and these are useful things for uncovering causation in the presence of fine-tuning. Okay, so if you want to try to, I mean, you may think, well, we've got this fine-tuning, maybe we can't see what causes what anymore, just from the observations. But if you consider the kind of sets of different interventions you can do and different combinations, then these are still very useful for uncovering causation, even in the presence of fine-tuning. Okay, so that's the kind of causal modeling part. So I didn't give full details here. There's just not enough time to do so. But I hope that gives, I mean, the main idea is that we essentially drop this requirement of the graph being acyclic, and we also drop the if and only if condition that d-separation implies independence, and just have it in one direction. Okay, now how do we get space-time into that? So at the moment we haven't mentioned this very much, or except maybe to provide a bit of intuition. And here I don't want it to be I want to treat it as an independent concept from the causal modeling. Okay, and that's because I want to, in principle, allow things like causal cycles or the kind of causation that if you take relativity theory maybe too strongly, you'll immediately rule out. Okay, but I do want to maintain a notion of relativity, because otherwise I'm going to get into all kinds of trouble with causal paradoxes and things like this. So in a sense, we're trying to minimize what we're taking, but while still staying hopefully on the safe side. Okay, so we just treat space-time as a second ordering, and at the moment it's completely independent of the first. So I'm allowing myself a priori to just assign space-time locations to random variables that in principle go against the way the arrow structure appears in the causal diagram. Okay, so you basically take all your random variables and you just give them coordinates, and maybe, let's just assume we're in Minkowski's space-time for the sake of simplicity. So we naturally have a notion of future, which is a second type of ordering that comes just from the space-time, from the light cone structure of the space-time. It doesn't have to be Minkowski space-time, but maybe that's the one that's simplest to think about. And now we can start allowing the causation to go against the space-time order in principle. And we want to do so in such a way as that we respect the relativistic principle that we're not able to superluminally signal, and that's what we call this a compatibility requirement. Okay, and so to state this, what we have is basically that if x affects y given do z, okay, so we already, given do z and w. So what this means is we can think about an agent who has access to information about an intervention on z, and also has access to w, and this agent also has access to y. Okay, then if x affects y given those things, it would mean that an agent with that information would be able to receive a signal from someone who's able to choose x. Okay, so by intervening on x, one agent could send a signal to another agent who has access to y, w, and knowledge about a previous, perhaps, intervention on z. Okay, and so if we want to prevent signaling, now this is the kind of motivation for the compatibility requirement. We better make sure that the joint future of z, y, and w is contained in the space-time future of x. Okay, because that means that when you have the ability to get together and see that the message from x is already in the future of x, and so we won't be able to have any signaling. Okay, so that's the underlying motivation. And so this is going to be the basic way that we get space-time into the picture in a way that we keep a notion of compatibility with relativity. So we're allowing causation outside the future as long as it doesn't allow signaling. Okay. And now let me give an example of the use. And so let's suppose here's a way to try and distinguish different forms of causation that all have the same correlations. Okay, so here's this diagram shows not only the causal model, but I've put the space-time picture on as well. So the blue things are show the light cone structures from each of the random variables, and the arrows show the causation. So here is the one-time pad. The first example is the one-time pad. So we have the random variable b. Okay, I've relabeled the variables from before just so that all the examples have the same labels. So now we have that b is the XOR of a and c, and all the parentless things I'm imagining are just bits with uniform distributions. So I'm not going to write that, but a and c are uniformly distributed, and everything is bits. Okay, here's the jamming situation. So in the jamming situation, or here's one way to set up the jamming correlations. We take a to be equal to lambda, so here are the causal mechanisms that would lead to jamming correlations, and we take c to be the XOR of b and lambda, and in the space-time diagram we have this, so a, b, and c are space-like separated. And similarly, we might have a causal loop. So here's an example of a causal loop. We take a as lambda, c is the XOR of b and lambda, and b is the XOR of a and lambda. Okay, and this is an example of a potential causal loop. And these three situations will all give rise to the same observed distribution, the same distribution over the observed variables. Okay, so the probability of a, b, and c is the same in each case. Actually, this is not so obvious for the last case. If you just look at the causal, these functional causal dependencies, they don't have a unique solution. So actually, I should be a bit more careful when I say that these have the same correlations, but we have a way to resolve this this lack of determinism that indeed does give that. And I think I did have a slide on that, but I think I'm going to skip it because I'm quite close to the end. Okay, so how would we actually distinguish these situations? Well, we're going to try and do so by interventions. So we're going to go in and we're going to start intervening on these variables and see what affects what. Okay. And without going through the details, these are the effects relations that we actually find. So in the first case, if we intervene on both A and C, we can have an effect on B. But if we intervene just on A or just on C, then there is no effects relation. Okay, that's because of the way the one-time pad is set up. And so what this means is that B should be in the joint future of both A and C. And indeed, that's how it's drawn here. Okay, secondly, we go to the jamming. In the jamming, the way it's drawn here, B can jointly affect A and C, but there's no single effects relations. But now the compatibility therefore requires that the joint future of A and C is in the joint future of B. Well, no, sorry, just the future of B. There's no joint in for B. And so, as you can see here, this is this shaded blue region, and this holds. So this would be an allowed space-time configuration for jamming correlations in this framework. And finally, in the case C, we have B affects A and C, but also AC affect B. Okay, and what this requires is that B should be in the joint future of A and C, and that the joint future of A and C is in the future of B. Okay, so this is the situation that looks a bit worrying. We've got a loop. Can it really be embedded in a reasonable space-time? Well, there is just a way to do it, which is exactly the way that's drawn. It's maybe not the nicest way to do it in the sense that we have to actually pick these coordinates extremely carefully. So there's not there's basically a measure zero set of space-time positions where we can actually achieve this. So that should already be quite a worrying thing, maybe, because that doesn't seem very natural. We've gone from one form of fine-tuning to another form of fine-tuning where we actually have to pick things extremely carefully. But actually, it's even worse than that, because this doesn't work in anything other than 1 + 1 dimensions. Okay, and the reason is that I need basically the intersection of the light cones of A and C here has to be equal to the light cone of B. But in higher dimensions, if you intersect two light cones, you don't get a light cone. and so actually this only works in 1 + 1 dimensions. So although I have got a causal loop, and this is embeddable in principle in a Minkowski spacetime, in fact, this seems to be a special property, just the fact that I'm in 1 + 1 dimensions. And we think, but actually it turns out to be a bit harder to see than you might hope, that this won't work in 3 + 1 dimensions.
And if you add one party, could you have A, C, and D, then the joint future light cone B, the future light cone of...
In 3 dimensions?
Yes,
no.
in more dimensions.
I still don't think you can do it. Yeah, yeah. Okay, so yeah, here's maybe some of the main... okay, this probably just summarizes what I just said, but these different effects relations allow us in principle to operationally distinguish these 3 possibilities that I just said. So the thing that differs is they have the same correlations, but they have different effects relations, and that allows us to sort of say which one is happening, and to think about then how to embed them into a Minkowski spacetime without allowing signaling. And yeah, the main point is that no superluminal signaling, in fact, doesn't directly rule out causal loops in our framework, although maybe it does if we're in 3 + 1 dimensions, which is probably the reasonable case to be thinking about. But it also, we can have this jamming situation, which is maybe not quite as scary as seeing a causal loop, where we can have causation without superluminal causation without superluminal signaling. Okay, yeah, and I already mentioned that. Okay, and so I think I'm basically towards the end of the time. So here's just a summary of what I've tried to say. So we have this framework, formally separates causal modeling notion from the relativistic notion. So if you want to ever think about retrocausation or causal cycles or anything like that, you're going to need some way to distinguish these two. So the framework allows this fine-tuning, and to have these cycles, we know we can use it to model several interesting situations, including jamming and this situation with causal loops, and we hope that it can be used, and I'm sure it can, much more widely. And these effects relations, or these higher order effects relations, are the kind of useful extra thing that allow us to detect this presence of fine-tuning of these causal influences. Okay, and there's a reminder of the links to the papers, but I think I'm out of time, so I should stop there and see if there are any questions.
Thanks, Roger. Very, very nice and clear talk. Yeah, questions?
Thank you for the really nice talk. So in the last slide, when you had these 3 pictures, in the last one, yeah, so if B is in the joint feature of A and C, and the joint feature of A and C is in the feature of B, and this can only happen if B is in the feature of itself.
So here, the joint feature of A and C is this blue light cone, and
yeah,
that's also the feature of B.
Yeah, so the last 2 sentences, that B in the joint feature of A and C, and the joint feature of A and C is in the feature of B. This could only happen if the B is in the feature of itself, like the feature of B is defined to include the event B itself, right?
Yes, yeah. Yes.
Yeah.
Yeah, I
So,
see what you mean. Yeah, yeah.
yeah.
So indeed, there's this. Yeah, B is really sitting exactly at the point where these light cones start intersecting, and indeed, yeah, the future includes the point itself, or so it's the inclusive future. Maybe it should.
Yeah. So if I think of this as events, so is there any interpretation of what that means for an event to be in the future of itself?
I think this is just a convention, whether you think of an event as in the future of itself or not, in a way. I mean, yeah. Yeah, I don't really know what else to say. I think you can just choose by convention which way you take it, but here you have to take it one way. So maybe it's not just a convention, but yeah.
Great. Maybe just one last short question. Yeah. Okay.
Thank you very much for the talk. I have a question concerning the term that you used, that B causes C. By that, you just mean that in this graph, you have a link from B to C.
Yeah.
Right. Now, I have a question concerning the scenario in the middle. Here we see that B causes C because from the functional relation of C, you see that B directly feeds into C, right? Yes, exactly. Now, is it conceivable that you could write down some other functional relations where maybe you have to view this graph as a subgraph of a bigger graph or something like that, where B does not really feed into C, such that you do have some causation in the graph, but you do not have actually any superluminal, well, I'm running out of terms, cause, influence, whatever happening. You know what I mean?
So it's certainly not like from the correlations that I've got. So I'm not sure I know exactly what you mean, but from the correlations I've got, I certainly don't have to draw the arrow like this. So there's kind of symmetry here. I can easily flip the arrow. B can point to A instead, or I could have some kind of mixture. I don't think if I've got to have functional relations underlying all this, I can get rid of any arrow from B, which I think is what you're hoping for, such that I can avoid.
The hope would be that maybe I embed this into some bigger graph or so, such that I can eliminate all arrows that are in a space-time picture superluminal.
Yeah, okay. I'm not sure that, I don't see how embedding it into a bigger graph will allow me to do that. It would certainly be nice if we could do that, but I don't think it's going to be possible in order to maintain the underlying, such that the underlying functional relations lead to the correlations that we're imagining here. But yeah, of course, if we could do that, then maybe we've got a much nicer resolution of this, because then we don't actually have to think about superluminal causation. But I think if you think about the correlations, they're really sort of must be superluminal causation in a way, right? I'm doing something here, and this either causes two things space-like separated with me to be correlated or anti-correlated. And it doesn't seem like I could do without some kind of superluminal causation to do that, unless I have a new notion of causation. So at least if I think in with this classical notion of causation, I don't think there's another way to do it. But maybe there's some higher notion of causation where this is naturally allowed, in the same way that when we try to explain the correlations that violate a Bell inequality, we don't say there's, it's a classical notion of causation with a fine-tuning. We say, there's some higher quantum notion of causation, and that's the right notion. So it could be that there's some higher notion of causation here, then that's the right notion. But I don't have such a notion off the top of my head. But thanks for the question.
Thank you very much.